Okay. So we're still with Newton's laws and some applications. We studied the car crash and the effect of seat belt last time. So today we are going to discuss the falling of objects in the presence of air resistance, مقاومة الهواء. So we studied before that if an object is falling down, it's affected only by the gravity. So its weight is mass times gravity, and its acceleration A, the acceleration equals to the gravity, which is 9.8. But this is not the real case. This is not the real case because there is also another force which is opposite to the motion, which we call it the air resistance. مقاومة الهواء. Air resistance is a force similar to the friction force. So it's always opposite to the direction of motion. Opposite to the direction of motion. So in case of an air resistance force, how to calculate the acceleration? The acceleration will no longer be g. It will not be 9.8. But as you are thinking right now, it's going to be lower than 9.8. Let's see how and why. Here I have two forces. The weight, which is mass times gravity, it's a downward force, and the air resistance, which is the opposite to the motion. Let's say the motion here is downward, so the acceleration is downward. So I will apply Newton's second law on this object. I will apply Newton's second law. Force equals, or the net force equals mass times acceleration. I will take the positive direction, which is the direction of acceleration. So I will take the weight to be positive and the air resistance to be negative. So weight minus air resistance equals mass times acceleration, and this is the equation of motion here. This is the equation that describes the acceleration of the object. Okay, guys? Weight minus air resistance equals mass times acceleration. If you want to get the acceleration in a side, so you need to divide over the mass. Okay, so it's W minus air resistance divided by the mass. You might simplify it more. You can say the weight is mass times gravity. Then you will divide mass times gravity over mass. This mass goes with this mass, so the leftover is G. And air resistance over M gives you air resistance over M. So at the end, you will find that what the acceleration equals G, which is 9.8, but minus something else, which is the air resistance divided by M. So this is a formula for acceleration in case of air resistance. Okay. If you neglect air resistance, like if in the problem he says neglect the air resistance, so the acceleration becomes what? 9, which is G. But if we don't neglect it, as in the real life, we will say that the acceleration is less than G. Acceleration is less than G. Sometimes it's 7, sometimes 5, sometimes 3. Okay. Depends on the air resistance. The more the air resistance, the less the acceleration. If the air resistance increases, the acceleration will decrease. And we can take the motion of the feather, feather الريشة, as an example for the air resistance. Okay, the air resistance on the feather is very, very high comparing to its mass. Okay, it's very high. So this amount is very high. So the acceleration of the feather will be very low. Okay. So this is an example for the effect of air resistance. So if there is an air resistance, like the case of this feather, the acceleration is what? G minus air resistance over M. But if you can neglect the air resistance, like in this example, here in this room, it's a vacuum room. Vacuum room means it has no air. No air. There are some pumps. We suck the air from the room and we keep it under vacuum. So in this case, there is no air resistance. And if you have a feather and if you have another object, both of them will reach to the ground at the same time. And both of them are affected only by the gravity because there is no air resistance in this case. Okay, guys? And again, this is only happen in the laboratory, like in the lab, في المعمل. But in the normal life, there is air resistance. So you have to use the equation A equals G minus air resistance over M. Unless in the problem he says there is no air resistance, or maybe he says consider it free fall. Free fall means also the air resistance is neglected. Okay? So the air resistance depends on what? Air resistance depends on the size and the shape, which I can abbreviate it as the area of the object. The area of the object. If you have a piece of paper, if you leave it as it is and you keep it to fall, okay, there will be a lot of air resistance. But if you fold it, okay, and if you make it smaller, if you fold the piece of paper, okay, and if you leave it to fall down, the air resistance will decrease. There are two tests in the picture. We have a plastic bag, this plastic bag. If you fold it and if you unfold it, when you fold it, the air resistance will decrease. If you unfold it back, the air resistance will increase. So if you increase the area, the air resistance increases. And from this property, they invented the parachute. You know the parachute, al-madalla? Okay. If somebody uses parachute in skydiving or when he jumps from an airplane or from the top of a certain mountain or building or whatever, okay, the parachute, because of its area, it increases the air resistance. And when you increase the air resistance, what happens? What happens when you increase the air resistance? The acceleration will decrease. Okay, so they move with very small acceleration, not the 9.8, but it may be 5, it may be 4, okay? It may be less than that. So this is the first factor, the area. So if you increase the area, the air resistance increases. Also the speed of the object. The speed of the object, it plays a big role in affecting the air resistance. The air resistance is proportional to the speed of the object square. And this comes from the experiments. They did a lot of experiments, okay, until they found that the air resistance is proportional to the speed square. So if you increase the speed a little bit, the air resistance will increase also, okay? So this is the other factor. So I need you to remember that if you increase the area, the air resistance increases. If you increase the speed, the air resistance also will increase. So these are the two factors. Okay, guys? I want you to look at the question.
Yes, على اللي فاتت.
Go ahead.
Doesn't the mass or the density of the object affect? Because if it was like a paper or a sheet of metal that has the same dimension and size.
The density of air, it plays a role. Density of air. The
And
more
the
the density, the more the
object.
air resistance. Density
How
of the
about the
object,
object?
it plays indirect role. Like if you remember here, there is mass in this equation. There is mass. Okay, so you are comparing between the air resistance and the mass of the object. Okay, so you look at the ratio of air resistance divided by the mass of the object. Okay, if this ratio is high, the acceleration becomes low. So the air resistance plays a role, and the mass of the object also plays a role. Okay.
Okay. And another question, please. Why is the V squared? Because when you are moving double the speed,
This comes from the experiments. This was done by experiments. by observing some experiments, and they found that it's proportional to the square of the speed, not the speed itself. Okay.
Okay, because I asked because
So
the number of molecules that are pushing on the object at double the speed is just double, not square.
yes, yes, you are right. You are right. So let's watch this video here and see what's happening for a skydiver. When the skydiver jumps from the airplane, his speed is still zero. So at the moment he jumps from the airplane, he has a zero speed. And we said the air resistance is proportional to the speed, or the speed squared. So if the speed is zero, that means the air resistance is zero. So the acceleration will be what? If the air resistance is zero, the acceleration is g, which is 9.8. So at the beginning, the acceleration is g. Why? Because the speed is zero. Why? Because the air resistance is zero. Okay? So this is at the first moment. But when he jumps, his speed will increase. His speed will increase. If his speed increase, what will happen? What will happen? The air resistance will increase. Okay? And the acceleration will decrease because the acceleration is g minus air resistance over m. So the air resistance will increase, the acceleration will decrease. Okay? But still there is an acceleration. It's not 9.8, it might be 7, 6, 4, whatever, but still there is an acceleration. So this causes the speed to increase also. The speed increases, the air resistance increases also, the acceleration decreases. So it's like they play, like they affect each other. Okay? Until the acceleration becomes zero. So the acceleration decreases until the acceleration becomes zero. This happens at which time? It happens when the two forces are balanced. Which two forces? The object is affected by two forces. We said weight downward and the air resistance upward. The weight does not change. The weight does not change, but the air resistance changes because it depends on the speed. So the more the speed, the more the air resistance. We started by zero, so it increases until it's equal to the weight. Until the air resistance becomes equal to the weight. In this case, we call them balanced forces. So the air resistance equals to the weight, or mass times gravity. At this moment, guys, at this moment, the acceleration equals what? Acceleration equals what? Equals zero. The two forces are equal, so the acceleration becomes zero. What does it mean, zero acceleration? It means that the speed will not increase anymore. It will maintain, or it will stay constant because there is no acceleration right now. So the speed increases, but the acceleration decreases. Okay, so they are to each other until the acceleration becomes zero. At that time, the speed will maintain constant. Okay, so this is in the first part of the skydiving. Let's watch it together and see what's happening. I need you to focus on what the speed of the object. This is the speed, and the weight is constant. You will find it here, and the air resistance you will find it here. There will be some arrows telling you about these amounts: the speed, and the air resistance, and the weight. Of course, the weight does not change, so you don't need to look at it. Let's try to start this video. So at the beginning, we will see. At the beginning, there is no speed, so the air resistance is zero. But the speed will increase. Now look at the speed. The speed increases. Okay. So let's look what will happen to the air resistance The air resistance will increase more and more and more until it's now equal to the what? The weight, and the speed becomes constant. The speed becomes constant. Okay, guys?
The same speed.
No, he's now falling with constant speed, 55 meters. The acceleration now is 0, and now he will do what? He will use the parachute. When he uses the parachute, what happened to the air resistance? It increased. Why the air resistance increased? The air resistance increased because of the area. He increases the area of the object. Okay? Let's try to let me try to do it again. Okay, now he's moving with constant speed. Why? Because the two forces are equal, and that means the acceleration is 0 and his speed maintains constant. So he will continue with this speed, but it's very high speed, 55 meters per second. So he cannot land, or he cannot reach to the ground with this speed. He has to use some aid like the parachute. When he uses his parachute, when he opens the parachute, what will happen? This will increase the area of the object, and we said the area is a factor. When the area increases, what will happen to the air resistance? What will happen to the air resistance? It will increase. When he increases the area, the air resistance will increase. So suddenly the air resistance becomes much bigger than the weight. That means the total force, or the net force, will be upward. That means there will be an acceleration upward. Okay, the net force is upward. That means the acceleration, there will be an acceleration upward. But in this case, I shouldn't call it an acceleration. I should call it what? What do you think?
Net force.
If the acceleration is upward, I should call it deceleration. I should call it deceleration because it's opposite to the motion. He is falling down while the acceleration now is upward. So the acceleration is opposite to the speed, or opposite to the direction of motion. So it's deceleration. What does it mean, deceleration? What does it mean? Slowing down. It means slowing down. So when he opens the parachute, the air resistance increases, the acceleration becomes upward, and that means deceleration. So let's look at the speed and see what will happen to the speed when he opens his parachute. Now, suddenly, in a moment, the air resistance increases and the speed will decrease. See, it will increase, acceleration becomes upward, and the speed will decrease very quick because of the deceleration. See? But there is another point. When the speed decreases, what will happen to the air resistance? When the speed decreases, what will happen to the air resistance?
It will decrease.
It will decrease again. So it's like a feedback. Okay. When the speed decreases, it will affect again the air resistance. So the air resistance will decrease more and more and more. And when the air resistance decreases, the deceleration also decreases. This negative acceleration or this deceleration will decrease until the air resistance is equal to the weight. So it was very big, but because of the speed decreases, the air resistance will decrease until it reaches back the same amount as the weight. So they will become in a balance again. They will come to a balance. the force, the air resistance, and the weight will be in balance. And this will cause deceleration to become zero, or the deceleration to become zero. Zero deceleration means what? It means a constant speed again. Okay, so let's watch. The speed decreases, so the air resistance decreases until it becomes equal to the weight, and the acceleration is zero. So look at the speed, constant speed again. Constant speed again, but it's very small speed. So now it's safe for this guy to land and reach to the ground. Okay, guys? So now everything is fine. Of course, when he reaches to the ground, there will be a normal force, but like it's not our point here. Okay, guys? So what I want you to know is he reaches to a constant speed, which is 55. Okay, this is before he uses the parachute. This speed, we call it terminal speed. Terminal speed. What is the terminal speed? It's a constant speed where the acceleration is zero. When the acceleration is zero, when the two forces are balancing each other, when the air resistance equals to the weight. Okay, so when the two forces are equal, the acceleration becomes zero and the speed will not change. It's not gonna increase anymore. Okay, like in our example here, it becomes 55. Then, when he uses the parachute, this will increase the air resistance, and the air resistance will do what? Will do acceleration. The deceleration will question here? Yes? Clear? Okay.
Doctor,
Yes.
I have a question.
Yes.
We had the same resistance and the same weight 2 different times, and we had 2 different speeds. Why?
Because at the beginning, the object was falling, so it was accelerating. The air resistance was very small, so it was accelerating downward. But after using the parachute, the air resistance is higher than the weight, bigger than the weight. Okay, and so in this case we have deceleration. So in the first half we have acceleration, then constant speed. Then after using the parachute we have deceleration, then constant speed. So acceleration, constant speed, deceleration, constant speed. Okay?
I understand that, but why the speed stop at 55 in the first situation, and then
Because
in the
there
second
was an acceleration.
Yeah, but why
That's what I
55?
say. No, it doesn't need to be 55. It might be 50, 60, doesn't matter. 55 is average for like an average mass or average skydiver. Okay? And 5 meters per second is like for average parachute. Sometimes the parachute is bigger, sometimes the parachute is smaller. Okay, but this is average numbers, like 55 or 5 doesn't need to be the same in all the cases. Okay?
Okay, thank you.
So let's try to solve this problem together. A 65 kilogram skydiver. So his mass is 65 kilogram. Reaches a terminal speed 55 meters per second. So he reaches to a terminal speed, so the speed is constant. And we said the speed is constant when is the speed is constant? Huh?
When weight equal
That's right. When the weight equals to the air resistance. Okay. And at this time, you need to know also that the acceleration is zero because the speed is constant. So she reaches to this terminal speed with her parachute unopened. So she hasn't used the parachute yet. Suppose the air resistance acting on here is proportional to the speed square. We said that before. The air resistance is proportional to the speed square. Or the air resistance equals to K times V square. You know that if there is two variables which are proportional to each other, that means the first variable equals to a constant times the second variable. Do you know that, guys? If two variables are proportional to each other, that means the first variable equals a constant times the second variable. I think you studied that in mathematics. If you don't, now you know it. Okay? This is the law of proportionality. So he says here, or he gives it to me here, that the air resistance equals to a constant, and he called this constant K. He called it K. I don't know why, but he called it K. Time is the V square. What is the constant V? He's asking what is the value of this constant. To find the value of the constant, you need to know the air resistance and you need to know the speed. The speed is given, 55, so it's not a big deal. 55 square. What about the air resistance? What is the air resistance here?
It's equal.
At the beginning. That's right. So the air resistance equals to the weight, which is mass times gravity. So mass is 65, gravity is 9.8. Because we are at the terminal speed, so air resistance equals to the weight. Now the only unknown is K, equals 65 times 9.8 divided by 55 squared, gives you around 0.2, or 0.21. Okay? So the right answer is number 1. Let's take another problem. At a given instant in time, a 5 kilogram rock, so the mass here is 5 kilogram, is observed to be falling with an acceleration. Let's stop reading. Mass is falling. So I might expect if it is a free fall, it will have acceleration equals to 9.8, which is the gravity, if this is a free fall. But here he says it's falling with an acceleration 7. So this is not a free fall. This isn't a free fall. But there is what here, guys? There is what? Air resistance.
Yes.
That's right, air resistance. And so this is a problem that has air resistance. What is the magnitude of air resistance up on the rock at this instant? We need to find the air resistance.
2.8.
So it's falling. So there's weight, mass times gravity. There's air resistance. Centimeter per second square. I need the air resistance. What do you think? If you remember the equation that we discussed at the beginning, you can use it. This equation. Where is it? Here. If you remember this equation, W minus air resistance equals mass times acceleration, or this one acceleration equals G minus F air over M, you can use it. Or you can do the equation by yourself. Like you can do it by yourself. Like let's say, start from Newton's second law. Net force equals mass times acceleration. Like let's just, I don't remember these equations. So I will take the direction of acceleration to be my positive. So I will say W minus air resistance equals mass times acceleration. The same equation. So the air resistance equals what? Take the mass times acceleration negative here, take the F air positive the other side, equals to the weight minus mass times acceleration. And as you know, the weight is what? Mass times gravity. So mass times gravity minus mass times acceleration. You can substitute, or somebody might say what? I will take the mass common factor. So it's G minus A. So he will get a new formula. Okay, so now you get a new formula for the air resistance. You don't need to memorize it. You can get it from the equation. It's not a big deal. Okay. So you can substitute mass of the object is 5 kilogram times g is 9.8 minus the acceleration is 7. The result will be 14 Newton. Okay, so if you memorize the equation, that's fine, or it's better if you can deduce it yourself. Questions? Do you have any question, guys? Understood? Okay. Using Newton's laws in the elevator المصعد. Let's suppose that someone, he has a scale. Scale means mizan, scale. He has a scale and he measures his weight inside this elevator. What are the forces acting on this scale? There is the weight of the person, which is mass times gravity. Okay, and there is also the normal force coming from the floor. So here I have two forces: the weight of the person downward, mass times gravity, and the normal force or the normal reaction of the floor upward. If the elevator is at rest, there is no acceleration. What will happen to the two forces? The two forces are balanced. So N equals to weight, right? So if the object is at rest, or if the elevator is at rest, the normal force equals to the weight. What is the purpose of the scale? Why do we use a scale? To measure our weight. But actually, the scale does not read your weight. The scales, they don't read your weight. But what's happening? They read the normal force. The scale reads the normal force, not the weight. But because you are at rest, the normal force equals to the weight, so its reading will be fine. It gives you the weight. That's fine. But what happens if the elevator has an acceleration? Will it be the same? No. Let's see. If I have an acceleration upward, if the elevator has acceleration upward, in this case, there is no balance. There is no balance. And you need to apply Newton's law. Net force equals mass times acceleration. Okay, guys? Where is the positive direction? It's the direction of acceleration. So I will take N to be positive and W to be negative. So N is positive minus W equals mass times acceleration. We are looking here for what? I'm looking for the reading of the scale, which is N. So I need to get N in a side, in the left-hand side, for example. N equals what? Take the weight to the other side, it will be positive. So it equals to the weight plus mass times acceleration. So the reading of the scale now will be false reading. It will give you a wrong reading. It will give you what? The weight plus mass times acceleration. So it gives you more than the right one. So it should, if it should give, for example, if it is at rest and it gives 100, it will give you 110, 115. Okay, so it gives you more reading, which is a false reading here. What if the elevator accelerates downward? If the elevator accelerates downward, I will do the same equation. The weight downward, I have the normal force upward, but in this case, the positive direction will be the downward one because of the acceleration. So I will do the same equation again. Net force equals mass times acceleration. Which one is the positive? The weight, because it's downward. So the weight minus normal force equals mass times acceleration. I'm looking for the normal force, the reading of the scale equals what? Take the normal force to the other side, positive, the acceleration to the left-hand side, negative. So the weight minus acceleration. So this is the force or the reading of the scale. So the reading of the scale here is also a force reading, but it's weight minus mass times acceleration. So it gives you less than the exact weight. So again, if the elevator accelerates upward, the reading will be more than the right weight. If the elevator accelerates downward, the reading will be less than the exact or the right weight. Some people, they like to simplify these equations. They say the weight is mass times gravity. So mass times gravity plus mass times acceleration. Take the mass common factor, so it's G plus A. So they get an equation for the normal force. And on the other side also it will be mass times G minus A. Okay? So if you try to simplify it, you will reach to this equation, which is, by the way, similar to the previous air resistance. This one, okay, similar. But the air resistance in our case here will be what? Will be the normal force. Okay, will be the normal force if the acceleration is down. Okay, so it's the same exactly. So let's try to study some problems. Do you have any question here, guys? For the reading of the scale upward, you feel that it's heavier, and downward you will feel that it's lighter. Of course, both of them are false. A 72 kilogram man, the mass is 72, standing on a scale inside an elevator, starting from rest, so its initial speed is 0. His mass is given. The elevator ascends, moves upward, so the acceleration is upward, attaining maximum speed 1.2 meter per second. So this is the final speed, 1.2 meter per second. In 0.8 seconds, what does the scale register during this time? We need the scale reading. Of course, the scale reading is N. If you remember the equation, can you say it? And the acceleration is upward. If you remember, the acceleration is upward, so it's what plus what? The weight plus mass times. Okay, or if you want to say mass gravity plus A, that's fine also. They are the same. I know the mass. I know the mass is 72 kilogram. I know the gravity 9.8. But what about the acceleration? How to get the acceleration? I know the initial speed. I know the final speed. I know the time. So acceleration is V final minus V initial over time. V final is what? 1.2. V initial is 0. Time is 0.8. Okay, so it's 1.2 divided by 0.8. 1.2 divided by 0.8. If you have a calculator, guys, try to do it. The result is what? 814. 814 Newton. Does anybody do it? Okay, 814. A student stands on a bathroom scale inside an elevator. It's very, very strange. Bathroom scale inside the elevator. So he stands on this scale in the elevator, which is at rest. Rest means what? The reading equals to the weight. The reading of the scale is the same as the weight. On the second floor of 5-story buildings, the scale reads 833. So this is the reading at rest. So this is the weight of the object. That means he tells you the weight, but indirectly. indirectly he tells you that the weight of the object is 833. Okay? As the elevator moves up, so I have the acceleration upward, the scale reading will become 936. It's normal. Okay? If the acceleration is upward, the reading will be more than the normal weight. So the reading, which is the normal force, equals 936 Newton, of course. What is the acceleration of the elevator? What is the acceleration of the elevator? Huh? Remember that the reading of the scale equals what? Huh? The weight, and you are moving upward, so it's plus ma, or you can say mg plus a, because you are moving upward. Whatever, you can use this one or this one. He needs here the acceleration, so I think it's better to use the first one, okay, because I have the weight and I have the normal force. So the normal force is 936, weight is 833, plus the mass. I don't have the mass, guys. Where can I find the mass? Where can I find the mass of the object?
Wait.
From the weight. From the weight, that's right.
Reading the
So
weight
the
over
mass is weight over gravity. 833 over gravity. Right. The weight over the gravity gives you the mass. Time is the acceleration. So you can find the acceleration. It will be 1.2 meter per second square. Okay, guys? A man weighs a fish with a spring scale. Spring scale, الميزان الزنبركي. Okay, it's this one here. It's we hang the scale and we hang the object that you need to weigh. So a man weighs a fish with a spring scale attached to the ceiling of the elevator. The ceiling of the elevator. By the way, the spring scale works exactly like the normal scale. But in the spring scale, I have the weight downward, and the upward force is not the normal reaction, but it's the tension of the spring. You can call it N, it's up to you to call it N or normal force, but actually it's the tension force, because this is a wire or cable, okay? So it's the same force, but usually I call it tension. Tension means shed, okay, or pull. That's how I do it in mechanics, but whatever name you call it, it's up to you. So it's the same exactly. I have the tension, T, which is the reading of the scale. If you want to call it N, it's up to you. As shown in the figure. While the elevator is at rest, again, at rest means what? The reading will be the weight. So at rest, it measures 40 Newton. So this is the weight. The weight is 40 Newton. And from the weight, we can get the mass. The mass is 40 divided by 9.8, the same like before. What weight does the scale read? What is the scale reading? If it accelerates upward at acceleration 2. So I have the acceleration upward and it's 2. I will do what? He needs the reading. The reading, T or N or whatever, equals what? Equals the weight plus mass times acceleration. The weight is 40 Newton. The mass is 40 divided by 9.8. The acceleration is 2. So it will be around 48.60. So in all the cases, the reading will be more than the exact reading. Okay? How much force does an 80 kilogram astronaut exert on his chair while accelerating straight up 10 meter per second square? So let's say he is here, okay, on a chair. Say this is a chair. Okay, there is the weight here and the normal force upward. Okay. So how much force does an 80 kilogram astronaut exert on his chair while accelerating straight upward? What do you think, guys? Here I have the acceleration is upward equals to 10. And I'm looking for how much force of the chair. So this is like the normal force. Okay. W plus mass times acceleration. So his weight is 80 times 9.8 plus mass times acceleration. The mass is 80 times the acceleration is 10. Or you can say mass times g plus a. If you want to do it this way, it's the same. So 80 times 9.8 plus 10, okay, gives you what, guys? Hmm? Can you do it, please?
A.
1,584 meters. That's right. So the first one. So these are some examples for an object that is moving with a certain acceleration, and we measure the normal force inside the vehicle or inside the elevator or inside the rocket, whatever. So I hope you enjoyed this lecture. So if you have any question, please